So this is quite an applied question. It tells you it's about the reactions of aldehydes, alcohols and carboxylic acids. And you need to think to yourself what functional group is changing, or functional groups are changing, and what reagents and conditions are needed for this change. So looking at it carefully, you can see it's an aromatic compound. When you have an OH group bonded directly to an aromatic compound, that's not an alcohol, that's a phenol. And the question is a bit misleading in the sense that it tells you about the reactions of aldehydes, alcohols and carboxylic acids. So an assumption people might have made is that that OH bonded directly to an aromatic ring is a secondary alcohol. It's not. It's a phenol. So you need to bear that in mind very carefully when you're thinking about what to do. So the aldehyde has become a carboxylic acid group. You can see that quite clearly. So that's an oxidation. So you need to think about what reagent might achieve that. If you draw upon your recall of alcohols and their reactions, you'll remember that aldehydes can oxidize under the influence of K2Cr2O7 in the presence of an acid, preferably H2SO4, to become a carboxylic acid. So the next part is to work out what compound C might be. So again, looking at the functional group you've got, it's a CHO, an aldehyde, and it's being subjected to NABH4, and that would mean it's reduced back to a primary alcohol. So don't put the OH group on a ring of any type, aromatic or otherwise, because it has to keep the carbon that was already in the aldehyde. So therefore you end up with a CH2OH attached to your aromatic ring at position number 1. You could argue that it might be position number 3. It doesn't matter what the position is, it's where it is in the diagram that's important, and also the fact it's CH2OH. So what happens now is you've got two separate compounds that will combine to make an ester. The primary alcohol on one will react with the carboxylic acid on the other to make an ester linkage between them. So I added my ester linkage. I've overemphasized it a little bit in blue so you can see it. Okay, so now we can go on to part 2 of this question, where they want us to do the mechanism for reaction 1. So if you remember, NABH4 reacts by nucleophilic addition. So you'll need some recall of the nucleophilic addition mechanism using the hydride ion as a nucleophile. And it's important to remember that you don't try to turn NABH4, the whole thing, into your nucleophile, which is what some people did. It's the hydride ion. So I'm going to put the hydride ion in blue and the rest of the mechanism in red, just to highlight it and draw your attention to it. So the first thing is, don't forget your dipoles on your carbon double bond oxygen. So 2 curly arrows are needed right here. One to show the nucleophile attacking the carbon, the delta positive carbon, and the other one to show the bond breaking in C double bond O. So the hydrogen that used to be the hydride ion has been added, and the oxygen atom is now negatively charged. So the next thing that happens is the lone pair on the oxygen moves towards water, and it actually moves towards the delta negative hydrogen, because that's partially positive, and as a result the oxygen-hydrogen bond in water can break. So finally you get your product of the addition, and then you need to have your OH minus ion as your side product. Okay, let's go on to the next and final part of the paper. So this final part was actually not done very well by many people, and it's because they mistook it for a simple recall question where you just kind of bring back what you learned about the structure of benzene when we first started teaching about aromatics. But it's not quite as simple as that. We have to look at the actual question. So let's make it a bit bigger and focus in on what it wants us to do. So they want us to describe with the aid of suitable diagrams showing orbital overlap the difference in bonding between structure A and structure B. So let's just clear up that this question is not asking you to recall a series of facts about why the Kekule structure, which obviously is structure A, of benzene is wrong, even though it's been printed in the question. And I think that's where a lot of people possibly got a bit confused. So orbital overlap can be shown in one or more different ways. So you've got localized overlap in one structure and delocalized overlap in the other. So what those two things mean is that the electrons stay between the two carbons in each carbon-carbon double bond. But in the structure B, the electrons are delocalized all around the ring. So something like that would do the job. Now, there's obviously a bit of space further down, as you probably remember. So let's see if we can put something in there as well. Don't forget it's 4 marks. So moving the page down a bit, we could maybe put a couple other things in here. So just moving the page down a bit so you can see what I've written. I've added that the p orbitals overlap sideways, but electrons are localized for structure A, and for structure B, p orbitals also overlap sideways, but the electrons are delocalized this time. So that should see you all right for that particular question. So you can see the emphasis and the nuance on what the question was asking was a little bit different to simply just recalling the facts. Okay then, I think that takes us to the end of the test and this clip. Hopefully it's been useful for you. Thank you for watching.